Hey everyone. So in this video, I like to introduce the notion of a vector. And so vectors can mean many different things depending on the context, but we'll look at vectors as a line segment with direction. And so I can imagine a vector as sort of the line segment between two given points, maybe let's say point A and a point B, and we sort of label the direction of this vector with an arrow. And here, because this vector starts at the point A and ends at the point B, we typically call point A an initial point, and we call point B a terminal point. And so, before we really dig into vectors, let me also introduce some notation for a vector. So, this vector that we have on the right here, sometimes we might label it with A, B, so the initial point, and then the terminal point, and we'll put a little arrow on top. So the first letter here is just the initial point, the second letter is the terminal point, we draw a little arrow on top. Sometimes we'll also label this vector with a variable, so we might say, hey, this is going to be u. This vector A to B is going to be the vector u, and we might also use a little arrow on top of that variable. So here we might say that vector is AB, we might call that vector u, and then sometimes we use in text boldface notation to denote a vector. So here I can't really use boldface notation with my tablet, so here instead of boldface I'm going to use blue. So here in text, vectors may be bolded, and so in this video, instead of bolding, I'm just going to use blue in this video. So here, instead of maybe labeling our vector with u and an arrow above it, I might just call it u, but I'll try to use blue to denote I'm talking about a vector. And so vectors can represent many different things, but typically they'll represent anything that can be described by both a size and a direction. So vectors can represent anything with size, both size and direction. And so, maybe one example that we'll definitely see in a later video is something like a plane trajectory. And so here, this notion of size of the vector, maybe I can imagine drawing a vector like so. The size of this vector might represent the speed in which the plane is traveling, and the way the direction the way the arrow is pointing might tell you the direction of the plane. Another thing that vectors are used to represent is the idea of force. And so maybe the intensity or the magnitude of the force will be denoted by the size of the vector, the length of the vector, how hard you're pushing an object, and then the direction of the vector is really the direction of the force. Which way the vector is pointing is telling you the direction of force. So intensity and direction of force. And then the way we'll commonly think of vectors is as representing displacement. So I can imagine, my arrow that is describing a vector. I can imagine that representing, how far I'm moving an object and the direction in which I'm moving that object. So in all of these examples that I described, the size or the length of a vector was one of the important pieces of information about that vector. And so we give this a special name. We say that the size or the length of a vector is called the magnitude. And so here, let's say I've got some vector. So from A to B, and let's say it's got length 5. Then we can describe the magnitude of this particular vector. We usually use kind of like the absolute value notation. We use these bars, we wrap it around the vector. So here I might say something like the magnitude of the vector AB is equal to 5, right? So this is just saying the size of our vector AB is equal to 5. Or I might say that this is my vector U, and I might say that the magnitude of our vector U, so I'll wrap this U in sort of absolute value notation, and I'll say that the magnitude of U is equal to 5. So these are two different ways of just talking about the size of our vector. So we use these kind of absolute value bars. So one thing that's very important to know about vectors is that when we have two vectors, we say that they're the same if they have the same magnitude and the same direction. That really, where they're positioned doesn't matter. Right, so if I have the vector here from A to B, well then this vector down here, although it has the same, or not the same initial point and the same terminal point, the fact that I try to do my best job in drawing in with the same distance and the same direction, the fact that this vector has the same distance and same direction as the vector A to B means that they are the same vector. And so here, I could even draw more examples where the goal here I'm trying to draw is that they have the same length and the same direction. These are all examples of identical vectors we call the same. And so it doesn't matter where we position these vectors, it doesn't really matter where the point A and the point B are, it just matters that the lengths and the directions are the same for these two vectors to be, or any of these vectors to be the same. And if I think about displacement as an example, let's say I'm moving a ball from point A to point B, it's not specifically the end points and the beginning points that make the vector, it's the fact that we're moving the ball in a particular direction and a particular distance. And all these vectors have that same distance and have that same direction, and they describe the same displacement of that ball. So we'll want to do mathematics on vectors. And the first thing that we should define is what it means to add two vectors together. And here, if I think about vectors as representing the displacement of some object, moving some object a particular distance and direction, then adding the two vectors represents sort of combining those displacements. Right? So in other words, if I want to think of the vector u plus v, well, the idea is that I take my vector u, so here's my vector u, and I can imagine it as sort of taking maybe a ball, for example, that started at this point, and I am moving it along, and it's ending at this point. And then if I add on the vector v, well, the idea is that I'm sort of taking that ball and moving it, in the direction of our vector v with the distance of our vector v. So here's my vector v, and now the ball has traveled this much further in the direction of v. And so u plus v is telling me that my ball started here, and it ended up at the end of our terminal point for v. This is the vector u plus v. Right, so here I'm just combining the two different displacements for u and v, and the ball started at the beginning of u and ended up at the end of v, and that's this u plus v. And I guess I should say that it doesn't matter what order we add two vectors actually. If I would have started first by moving my ball, or displacing my ball by the vector v, and then displacing my ball by the vector u, I can draw it a little bit better, it's angled upwards a little bit more. Here's my vector v, or vector u. Well then, the vector v plus u is really the same vector as u plus v. Right, so it doesn't matter where this red vector is positioned. Here the fact that these two red vectors have the same distance and the same direction means that they really represent the same vector. They describe the same displacement of a ball, for example. And so here, if I want to add two vectors, well, I sort of just kind of stack one on top of the other, beginning to end. And here, u plus v is the vector from the beginning of u, or from the initial point of u to the terminal point of v after we've stacked one vector on top of another. And we've said that here v plus u gives us the same vector. It doesn't matter how we add, or the order in which we add two vectors together. Okay, so we talked about adding two vectors together. What does it mean? What should it mean to scale a vector? Let's say, I've got my vector u here, and I want to think about what it might mean to have the vector 2 times u. Well, 2 times u, typically when we think about 2 times a number, it means to double that number, add that number to itself. And that should be the same with vectors. Right? So 2 times u should represent the vector obtained by taking the vector u and doubling it, or adding it onto itself. Right? So stacking the displacements. We're stretching this vector by a factor of 2. So that's really how we should envision this vector 2 times u. It's really just stretching this vector by a factor of 2, doubling it. It's going in the same direction, just twice as far. And then here, what about something like negative u? Well, here this vector should have the same length, just going in the opposite direction. So here, negative u, it's the same vector, just pointed in the opposite direction. Same length, just other side. And then if we add something like 1/2 times u, well, this just compresses our vector by a factor of 1/2. So here it's kind of shrunken or cut in half, so maybe something like this. Just to have a rough idea or some intuition for what the vector 1/2 u might mean. But in general, scaling a vector, all that does is stretches or compresses the vector by the given factor, by the factor, or the coefficient. And another thing to emphasize is that multiplying a vector by a negative number, all that does is reverses the direction of the vector. Like we saw above. So here, let's combine these ideas to think of what the vector u minus v should look like. And so here I've got a vector u, I've got a vector v. And so what should u minus v look like? Well, u minus v, this is really the same thing as u plus negative v. And we know what u looks like. What does negative v look like? Well, negative v looks like the same vector as v, but just reverse, right? Written in the opposite direction, drawn in the opposite direction. This is negative v. And so how do I add these two vectors? Well, I kind of stack one on top of the other, put the initial point of one on the terminal point of another. So here I've got my vector u. Maybe it looks something like this. So here's u. I'm going to add on negative v to it. Well, negative v looks like this. Right. Drawing my straight lines always come out so wiggly when I draw on this tablet, especially when I draw slow. Okay, but that's the idea of u, and that's the idea of negative v added onto one another. And so u plus negative v, or u minus v, is this vector we obtain from starting at the beginning of u and ending at the beginning, or ending at the end of negative v. This is u plus negative v, or u minus v. So here, maybe I'll just draw it off to the side unit, sort of away from the rest of this picture. This is the vector u minus v. And so really here we're just combining the ideas of adding vectors and then also the idea of negating a vector or flipping its direction. So in all of the examples so far, we've just described what a vector is geometrically, how to add vectors geometrically, how to subtract vectors, scale vectors geometrically. But it's hard to be very precise with pictures and geometry sometimes. And so, what can we do to fix this? How can we do math with vectors? Well, we can be a little bit more precise by, describing a vector by its horizontal and vertical displacements. This will make things a little bit more concrete. And so here, this is typically called component form. So if we're describing the horizontal and vertical displacement of a vector, this is called component, the component form of a vector. Right, so here maybe I'll just draw a quick picture, is that here if I have some vector u, well here we can be precise about this vector by describing the horizontal displacement from its initial point to its terminal point. Maybe I'll call this A. And we can describe the vertical displacement given by this vector from its initial point to its terminal point. I'll call this vertical displacement B. So we can represent u by both of these displacements together. So here it's often written as in sort of these pointed brackets or angled brackets. It's horizontal displacement, comma, it's vertical displacement. And so here sometimes we'll call this first quantity, we'll call this the horizontal component of the vector. And we'll call this second quantity the vertical component of the vector. And so one thing I really want to note here is that this looks a lot like a point, how we describe points, but we give this vector some slightly different notation. We don't use parentheses, we use angled brackets to know we're talking about a vector. I want to emphasize that here, A comma B in angled brackets, this is not a point. Right, so points describe specific positions. Vectors, they don't really care about positions, they just care about distance and direction. And so this is a very different idea from a point. And so really, this vector, these horizontal and vertical components, they just describe how to get from an initial point to a terminal point. They just tell you that to get from the initial point to the terminal point, of our vector, we should travel A units horizontally and B units vertically. Right, so it's not really fixed to any particular position, it's just telling us how much we should move left or right, up and down, so that we're really describing the initial point and the terminal point of our vector. And so I have this vector here, I've labeled v, and I want to write down the component form of this vector. And so what is the component form? Well here, I've got its initial point, I've got its terminal point, and the component form is just telling me, how far this vector travels left to right, and how far this vector travels up and down to get from the initial point to the terminal point. And so here I can see that left and right, this vector travels 3 units, right? So here we've got 3 units, and then up and down to get from the initial point to the terminal point, this vector is traveling -5 units. So really I can represent this vector in component form as the vector 3, -5. Now what if we have another example here where we're given the vector, so we're given that the vector, the component form of the vector is -2, 4, and we know that the initial point of this vector is -1, -2. Okay, so here this just says that we're sort of starting at this point, -1, -2, that's the initial point, and we know that our vector, it has a horizontal component of -2, so travels 2 units to the left to get to our terminal point, but it also travels 4 units up to get to our terminal point. And so here, this is the location of the terminal point. And so this is our vector u. And so earlier we talked about what it means for two vectors to be equal. I should also add here that two vectors are equal if their components are equal. Right, so it doesn't matter where they're positioned, where the initial point is and where the terminal point is, just as long as their horizontal components are equal and their vertical components are equal, then that really means that the two vectors are traveling in the same direction with the same distance. So now that we have the idea of component form for a vector, we can also be a little bit more precise about what it means to find the magnitude of a vector. So here, let's say I've got some vector u, and here that we can see that the horizontal component of this vector u, we'll call it a, and here's the vertical component of this vector u, I'll call that b. Well, how do we find the magnitude of a vector from its components? And again, remember that magnitude, this just represents the length of the vector. So, the distance between this initial point and this terminal point. So how do we find this magnitude? Well, here we can see this right triangle that sort of fits in this picture. And really the magnitude of the vector is the same as the length of this hypotenuse in this right triangle. And so we can use the Pythagorean theorem to find the magnitude of this vector. Right, so here this just says that, if I write down the magnitude of the vector, or in other words, the hypotenuse of this triangle, we know that the hypotenuse squared is equal to, well, the square of this leg lengths added together. So a squared plus b squared. Right, so here a was the horizontal component and b was the vertical component. So we square these, add them together, we get the square of the vector length. And so if I just want to write a formula for the vector length, I'm going to take the square root of both sides, and I'm going to get that the magnitude is equal to the square root of a squared plus b squared. Right, the sum of the squares of the components, the horizontal components and the vertical component. So let's use this idea to find the magnitudes, or the lengths of the vectors of u and v, where u and v were the vectors in one of the previous examples. So u is the vector -2, 4, and v is the vector 3, -5. So again, here we're just using the Pythagorean theorem, really. The magnitude of u, well, this is equal to the square root of the sum of the squares of the components, right? So this is -2 squared plus 4 squared. Now this comes out to be the square root of 4 plus 16. This is the square root of 20, which we can write as the square root of 4 times the square root of 5. And the square root of 4 we can evaluate as 2. The square root of 5 we can't do much better with. So the magnitude of u is 2 square root 5. So all we did was we squared the components, we summed them together, and we took the square root. And so what about the magnitude of v? Well, this is equal to the square root of 3 squared plus -5 squared. Right, so this is going to give us the square root of 9 plus 25, which is the same as the square root of 34. And there's no perfect square that divides 34, so this is as good as we're going to get. So if we go back to the previous example that included these vectors u and v, well, really what we've found is that the magnitude of the vector u we said that this was, maybe I'll put the magnitude here, this was equal to 2 square root 5, right? This is really just using the Pythagorean theorem on this right triangle with horizontal component -2 and vertical component 4. Now if we go back to our other example, or I guess that's above, is that if we have the magnitude of v is equal to, what did we get? We got the square root of 34. And again, this was just using the Pythagorean theorem on the right triangle, where the leg length, the horizontal leg length, is 3. That's just the horizontal component of the vector. And the vertical leg length is -5. That's the vertical component of that vector. Okay, and so how do we add two vectors that are in component form? Well, it's exactly what you expect. So what we do is we take the vertical components and we add them together, and we take the horizontal components and we add them together. So here if I have vectors u and v with their horizontal component a1 and a2, well then I just add those horizontal components together, and their vertical components are b1 and b2 respectively. Well, I just add their vertical components together to get u plus v, a vector for this. And so, this should make sense. Maybe I can draw a picture to really illustrate this. So here's my vector u. Here's my vector v. And here's the vector obtained by adding these two vectors together, right? They sort of start at the beginning of the first vector, and at the end of the second vector. This is u plus v. And so what's the horizontal component of this new vector u plus v? Well, it's this distance here, right? The horizontal distance of this, this red vector. And here that's really just made up of the horizontal distances of the two different vectors, right? So here, right, so a1 was the horizontal distance of, or component of u, a2 was the horizontal component of v, and so a1 plus a2 is going to give us the horizontal component of u plus v. And then similarly, the vertical components of these two vectors added together is this distance here, and really I can see that really, the vertical component of u, that was b1, that's this distance here. The vertical component of v is b2, and so adding these two together gives us, we can see the vertical component of u plus v. And so here, this is just an illustration to prove that u plus v is exactly what we expect. We just add the corresponding components together. And what about scaling vectors? Let's say I take some number c and I multiply it to my vector u. Well, here this just takes my vertical component, my horizontal component, and I multiply each of them by this constant c. So here really this is c times a1, and then c times b1. I just scale each component when I scale my vector. Okay, so let's use all these ideas to find the vector 3u minus 5v, as well as the vector 4u plus v, with these vectors u and v as -3, -2, and 4, 6. So I definitely encourage you to pause the video and try this example out yourself first, and we'll go over together in a moment. So 3u minus 5v, well, this is like taking my u vector, -3, -2, and here I'm going to scale it by 3. And then I'm going to take away 5 sets of my v vector. So here the v vector is 4, 6. And so here scaling my vector u, right, that just means multiplying each component by that scaling factor. This gives us -9, -6. And then here scaling 4, 6, my vector v, by -5 gives us, it's going to give us -20, -30. So I'm going to include that, I'm going to distribute that negative in, and then just think of this as adding two vectors now. And so here when I add these two vectors, I just add each of their components. I'm going to add the horizontal components together to get -29, and then I'm going to add their vertical components together to get -36. So that's my vector 3u minus 5v. And then next we wanted to find, well, what was it? It was 4u plus v. 4u plus v. And so this is equal to, this is like taking 4 sets of my u vector, so -3 comma -2, and adding it with 1 set of my v vector, that's 4 comma 6. And so 4 sets of my u vector, that's -12 comma -8. And 1 set of my v vector, well, that's again just 4 comma 6. And adding these two quantities together gives us, well, here we add the horizontal components to get -8. We add the vertical components to get, what is this? This is -2. This is our vector. Our vector comes from the combination of u and v, 4u plus v. And so geometrically here, I didn't draw a grid or anything, but geometrically here, what does 4u plus v mean? Well, it means I take 4 sets of my u vector. So u is the vector -3 comma 2, so it looks something like this maybe. But a little further out left and then a little bit down. This is my vector u. And 4 sets of u kind of looks like just stretching this out by a factor of 4. Right, so maybe 4 times this vector u. And then here, so here maybe I'll write this down as 4u. This is 4u. And then adding on our vector v is the vector 4 comma 6, right? So 4 units to the right, 6 units up. Maybe it looks something like this. And so, the vector 4u plus v, that's this vector here. So here, just to give you some sense geometrically of what we're doing with this computation, is we're obtaining this new vector that starts at the beginning of 4u and ends at the end of v that's stacked onto 4u. So this is our vector 4u plus v, and it looks about right? So here we said that it's -8 comma -2, and it looks like it's going far out to the left and a little bit down. So sometimes we give a little bit of extra attention to really the most basic vectors out there, the vectors 1 comma 0 and the vector 0 comma 1. So what are these vectors? Well, here this vector on the left, that's the vector with 1 unit distance to the right, no vertical component. It's not moving up or down. And then here the vector on the right, this is the vector that's 1 unit in the up direction with no horizontal component. And so, why do we give these two vectors a little bit of extra attention? Well, that's really because every vector out there, every vector in the plane, can be written as the sum of these two vectors. And so for that reason, we give these two vectors a little bit of extra attention. We even give them names. Sometimes we'll call this vector on the left I, and we'll call this vector on the right j. And so, if we take one of our vectors from the previous example, u is equal to the vector -3 comma -2. Well, really, if I wanted to express this in terms of our two special vectors here, I could write this as -3 sets of 1 comma 0 and -2 sets of the vector 0 comma 1. Right, so here what this is really saying is that my vector u can be rewritten as -3 sets of the vector I added on with -2 sets of the vector j. So this is another form you'll see vectors in, is sort of in terms of these two special vectors I and j. This is quite a common way to write vectors, and it's really equivalent to the way we've been describing earlier. And maybe just to do this for our other vectors as well, so v, earlier we said v was given by the vector 4 comma 6, and really this is the same as 4 sets of I, the horizontal vector of length 1 and going to the right, plus 6 sets of the vector j. So 4i plus 6j, this is the same as the vector with a horizontal component 4 and a vertical component of 6. And these are two different ways of expressing the same vector. And so let's say u represents the vector I minus j, and v represents the vector negative 2i plus 3j. Let's find the vector 4u plus 2v. Well, here the vector 4u plus 2v, this is equal to 4 sets of our u vector, and u is the vector I minus j. And then here we're adding 2 sets of our v vector, and our v vector, that's negative 2i plus 3j. And so we can just distribute our 4. We get 4i minus 4j. And we can distribute our 2, giving us, well, here that would be minus 4i plus 6j. And then we have some like terms here, right? So here we can combine these horizontal components, these horizontal vectors together, and we can combine these vertical vectors together to give us, well, that'd be 0 sets of I and 2 sets of j, so 2j. And so all this says is that if I take 4 sets of u and add it on with 2 sets of v, this is really equivalent to the vector that's 2 units upwards. This is really the same as vector 0, 2.